Environmental and safety considerations. Emissions of greenhouse gases and air pollutants. Hydrogen can be used with zero or near zero emissions at the point of use. When hydrogen is burned in air, the main combustion product is H2O with traces of NOx, which can be controlled to very low levels. No particulates, carbon monoxide, unburned hydrocarbons, or sulfur oxides are emitted. With hydrogen fuel cells, water vapor is the only emission. Moreover, the total fuel cycle emissions of pollutants and greenhouse gases, such as CO2, which could contribute to global climate change, can be much reduced compared with those of conventional energy systems. Fuel cycle emissions are all of the emissions involved in producing, transmitting, and using an alternative fuel. For example, for hydrogen made from natural gas, there would be emissions of CO2 and NOx at the hydrogen production plant. Emissions associated with producing electricity to run hydrogen pipeline compressors. The nature of these emissions would depend on the source of electricity. And zero local emissions if the hydrogen is used in a fuel cell. The more efficient the in-use device, e.g. a fuel cell vehicle, the lower the fuel cycle emissions per unit of energy service, e.g. emissions traveled per mile. Total fuel cycle emissions of greenhouse gases and other pollutants have been estimated for hydrogen vehicles by several authors. The total fuel cell carbon emissions per kilometer are shown in Figure 13 for gasoline, methanol, and hydrogen used in mid-size automobiles powered by internal combustion engines or fuel cells based on estimates by Williams et al. Man, that et al. Guy is everywhere. Various primary resources are considered for hydrogen production: natural gas, biomass, coal, solar energy, wind, and nuclear resources, and methanol production, natural gas, biomass, and coal. The effect of sequestration of carbon is shown for hydrogen production from natural gas, biomass, and coal. Emissions are indexed to a future, efficient gasoline-powered internal combustion engine in a 4 to 5 passenger automobile with a fuel economy of 42 miles per gallon of gasoline based on Ford's aluminum-intensive design. Emissions from a current 26 mile per gallon gasoline internal combustion engine vehicle are shown as well. Fuel economies for fuel cell vehicles are taken to be 71 miles per gallon equivalent for gasoline with onboard partial oxidation reforming, 69 miles per gallon for methanol with onboard steam reforming, and 106 for hydrogen. 106 miles per gallon for hydrogen, eh? With hydrogen from natural gas, the most likely near-term feedstock, greenhouse gas emissions from a hydrogen fuel cell-powered vehicle are reduced by more than 60% as compared with an efficient future gasoline internal combustion engine vehicle. CO2 emissions can be reduced by another 20% if the CO2 is separated during hydrogen production and then sequestered. With hydrogen from coal, the fuel cycle emissions for a hydrogen fuel cell vehicle are reduced 30% as compared to a gasoline internal combustion engine vehicle. With carbon sequestration, fuel cycle emissions from coal-generated H2-powered fuel cell vehicles are only 30% of those from gasoline internal combustion engine vehicle. If hydrogen is made from renewable energy sources such as biomass, solar resources, or wind, the fuel cycle greenhouse gas emissions are virtually eliminated. Emissions from electrolytic hydrogen production depend on the source of the low-cost electricity. In cases such as Brazil, where the source is hydropower, greenhouse gas emissions should be essentially zero. The United States, where the marginal generation mix includes coal-fired power plants, life cycle CO2 emissions for hydrogen-powered transportation can be substantial, exceeding those of gasoline. With biomass, hydrogen, and carbon sequestration, it would be possible to have a net negative carbon balance. Carbon would be removed from the atmosphere. It would be possible to envision a future energy system based on hydrogen and fuel cells with little or no emission of pollutants or greenhouse gases in fuel production, distribution, or use. Woo! Reiterate that one. With hydrogen, we can go carbon negative for the transmission sector. Did not expect that. Resource land and water use for hydrogen production. Can hydrogen be produced sustainably? As mentioned above, there are a variety of primary sources that can be used to make hydrogen. Over the next few decades, and probably well into the next century, fossil sources, such as natural gas or coal, may offer the lowest cost in many locations, with small contributions from electrolysis powered by low-cost hydropower. If the fuel decarbonization or carbon sequestration route is pursued, underground storage capacities for carbon dioxide in deep saline aquifers may be as much as several hundred years at present CO2 emission levels, or more. In the longer term, or where locally preferred, renewables such as waste, biomass, solar resources, or wind might be brought into use. It's been estimated that hydrogen derived from biomass produced on about 2/3 of currently idled cropland in the United States would be sufficient to supply transportation fuel to all of the cars in the United States if they use fuel cells. Wow. Municipal solid waste could be gasified to produce transportation fuel for 25 to 50% of the cars in the United States metropolitan areas. Solar and wind power are potentially huge resources for electrolytic hydrogen production, which could meet a projected global demand for fuels. Although the delivered cost is projected to be about 2 to 3-fold that for hydrogen from natural gas. The collector area required for photovoltaic hydrogen production for one hydrogen fuel cell car is 25 square meters, assuming average U.S. installation. Assuming U.S. installation. I'm just surprised. It's been estimated that projected global 2050 fuel demands over 300 e-joules a year could be met by solar hydrogen produced on 0.5% of the world's land area. If 14% of deployable wind power in the United States were used to produce hydrogen, this could power all U.S. cars, assuming they were run on hydrogen fuel. This is blowing my mind. Safety issues. When hydrogen is proposed as a future fuel, the average person may ask about the Hindenburg, the Challenger, or even a hydrogen bomb. Clearly, consumers will not accept hydrogen or any new fuel unless it's as safe as our current fuels. In this section, we discuss hydrogen safety, in particular, as compared with fuels like natural gas and gasoline, which are accepted today and have good safety records. Table 5 shows some safety-related physical properties of hydrogen and natural gas and gasoline. In some respects, hydrogen is clearly safer than gasoline. For example, it's very buoyant and disperses quick from a leak. Experiments have shown that it's difficult to build up a flammable concentration of hydrogen except in an enclosed space because the hydrogen disperses too rapidly. This contrasts with gasoline, which puddles rather than disperses, and in which fumes can build up and persist. Hydrogen is non-toxic, which is also an advantage. Other aspects of hydrogen are potentially safety concerns, especially its wide flammability limit and low ignition energy. Hydrogen has a wide range of flammability and denotes limits, e.g. a wide range of mixtures of hydrogen and air will support a flame or an explosion. In practice, however, it's the lower flammability limit that is of most concern. For example, if the hydrogen concentration builds up in a closed space through a leak, problems might be expected when the lower flammability limit is reached. Here the value is comparable to that of natural gas. The ignition energy, e.g. energy required in a spark or thermal source to ignite a flammable mixture of fuel and air, is low for all three fuels compared with that of commonly encountered sources such as electrostatic sparks. The ignition energy is about an order of magnitude lower for hydrogen than for methane or gasoline at stoichiometric conditions, e.g. at the mixtures needed for complete combustion. But at the lower flammability limit, the point where problems are likely to begin, the ignition energy is about the same for methane and hydrogen. Safe handling of large quantities of hydrogen is routine in the chemical industries. Proposed use of hydrogen in vehicles has raised the question of whether this experience can be translated into robust, safe hydrogen vehicles and refueling systems for the consumer. Several recent studies have addressed this question. In 1994 hydrogen vehicle safety study by researchers at Sandia National Laboratories said there is an abundant evidence that hydrogen can be handled safely if its unique properties, sometimes better, sometimes worse, and sometimes just different from other fuel cells, are respected. A 1997 report on hydrogen safety by Ford Motor Company concluded that the safety of a hydrogen fuel cell would be potentially better than that of gasoline or propane vehicle with proper engineering. To assure that safe practices for using hydrogen fuel are used and standardized, there has been a considerable effort in recent years to develop codes and standards for hydrogen and fuel cell systems. The US DOE, through the National Renewable Energy Laboratory, NREL, the National Hydrogen Association, a hydrogen industry group in the United States, and the International Energy Agency, all have ongoing hydrogen codes and standard activities. NREL has helped organize a United States-Canadian expert group, which is developing a hydrogen safety source book. The National Fire Protection Agency in the United States and the International Standard Organization, ISO, are currently developing hydrogen standards. In addition, fuel cell vehicle manufacturers are developing recommended practices for fuel cell vehicles and hydrogen systems as part of fuel cell vehicle demonstrations. So my takeaway from that is hydrogen's safer than what we use.